organic chemistry?
Sorry.
Is this chapter about dancing resonance and back bonding of organic chemistry?
Yes, we will study about dancing resonance over here. And back bonding is basically mesomeric effect only.
Yes.
So about the structure, so carbocation, it has 3 valency and a vacant p orbital, and it is cation, so positive charge. So if I count number of electrons, there are 6 electrons, right? That means it is, yes, electron deficient. And since it is electron deficient, it will be your electrophile, means it will be accepting electron density. So it is electrophile also. Then if we say what is the hybridization of this carbon, it is sp2 hybridized. sp2 hybridized means it is diagonal planar. The structure is diagonal planar. Okay, this is whole about this structure of carbocation. Now let's move on to the important part, that is the stability of carbocation. Now I'll be discussing about the effects that which stable your carbocation. So I'll be writing in the priority order only. Okay, so the first effect, that is the mesomeric effect. So if I have this example, CH3 OCH2 positive charge. Okay. And I have this one, benzene, having CH2 positive charge. Okay. Now, in this case, you have oxygen. And I have told you one thing, whenever you have any lone pair donating species adjacent to the carbocation or double bonds or benzene, then it will have a tendency to donate the electron density and show plus M effect, that is plus mesomeric effect. In this case, you have resonance, correct? You have resonance from 3 pi bonds, but it is just a resonance. Hence, mesomeric effect will be more stabilized, because if you just draw the resonating structure of this mesomeric effect, you will say it is CH3O positive charge double bond CH2, right? And here if you count all the electrons, basically all the atoms have complete octet, 8 electron of this oxygen also, 8 electron of this carbon also. But when you make a resonating structure of resonance, here you will be getting definitely a carbocation. So here, if you have this one, so this has now 6 electron. Firstly, it was having 6 electron. Now this carbon has 6 electron. So no, it is not stable as it was unstable for the mesomeric effect. So this is example for mesomeric. Just note it down. Then we'll discuss it more. Done. Okay. And today I will share the CPP of this GOC chapter. So just go through the notes firstly, revise them, and then try to solve the CPP or your package. You will be easily able to do them. Okay. Now the second effect. Second effect, aromaticity. If I have this compound, what is the name of this compound? I have told you all. What is the name of this molecule? In the exam, you will not get the structure, you will get the name because the name is very important. Tropylium cation. 7-membered ring, tropylium, charge is positive, cation, tropylium cation. Okay. Now, see, here my positive charge is stabilized by aromaticity. It is aromatic molecule, right? And this positive charge is just stabilized by resonance. So you will give aromaticity more parity than the resonance. Okay. This is my second point. Aromaticity will be more stable. That cation that is involved in aromaticity will be more stable than your resonance part. Okay. Then the third part, if you have resonance, the third is resonance. If I have again this molecule only, I'm taking this reference molecule for the resonance. So if I have this one and I have only this one cation, so now this is more stable because again it is having resonance. And in this case, you are only having 3 alpha hydrogen means hyperconjugation. So hyperconjugation is a lesser effect than the resonance. So my fourth category is will be your hyperconjugation. So hyperconjugation, if you have CH3, CH2 positive charge and only CH3 positive charge. So in this case, you have 3 alpha hydrogen means there is hyperconjugation. But in CH3 positive charge, you don't have any hyperconjugation. So you only have the inductive effect of hydrogen, you can say. So yes, this will be more stable because this has 0 alpha hydrogen. Clear. Now the last point, that is the inductive effect. The last effect, inductive effect, in this, if you have CH3, CD3, CT3, tell me the order, which one will be more stable? CT3. Correct, correct. CT3, because tritium has more plus side effect than your hydrogen or deuterium. Just note this down. This priority order you have to remember. Okay. So just note down these examples. These are all your homework. Again, you have to see just the order and then you have to give the answer. Okay, I'll be explaining the first question so that it will be easier for you to solve the second, third, and fourth. Just note them. See the first explanation of first question. See, this carbocation, so basically you have to see now the every factor, resonance, hyperconjugation, and firstly write down and then compare between them. So see, this carbocation is stabilized by 4 hydrogens, 4 alpha hydrogens. So it has hyperconjugation. So I can write down this is having 4 alpha hydrogen. Also, you can notice there is phenyl, so it will be resonating with phenyl ring. So I can say it is resonance. It is doing resonance with 3 pi bonds also. So resonance with 3 pi bonds. Okay, this is the stability effect of this carbocation. Now for this carbocation, you have phenyl, so 3 pi bonds, correct. Then you have two alpha hydrogen from this side. Now you can see from this that it has an extra alkene, right? So you can have resonance and you can make one more resonating structure of this, like phenyl will be over here only, but now double bond over here and carbocation will come over here, right? So firstly, it was having 2 alpha hydrogen from first structure. In the second structure, you are again having these two as alpha hydrogens. So in total, it is having 4 alpha hydrogen. Correct? So you have to make the resonating structures also. Then you have to compare. So 4 alpha hydrogen in total. And in total, if I ask how many pi bonds are resonating with this carbocation, there are 4. Because 3 from the benzene ring and 1 extra from alkene. So there are total 4 pi bonds. That means I can say one thing, that second one is more stable than first one, right? This is the 1, 2, 3, 4. So my first order that I can conclude, that second one is more stable. Okay. Now come to the structure. Again, you have phenyl ring, you have carbocation, 2 alpha hydrogens over this. So you have 2 alpha hydrogen and 3 pi bonds, and extra pi bond is this. So extra 4 pi. Done. Now you have to make the resonating structure. So when you make the resonating structure, you will get phenyl, oxygen, carbocation over here. Now tell me, oxygen will apply which effect over here? Which effect?
Plus
Harshini,
I.
you are not audible. Sorry.
Plus I.
Plus I, not plus I, plus M, mesomeric, because it can donate its electron density to the vacant orbital of your carbon. So it will be plus M effect. And I have told you one thing, that whenever you have plus M effect, it will be the highest stable carbocation. So I can say one thing, that since it is having alpha hydrogen that are less, pi bonds same, but it is having extra plus M effect, that means 3 is the most stable. Okay, now I have to see the fourth one. Fourth one is the aromatic molecule. So yes, mesomeric, then aromaticity, then hyperconjugate, then resonance, and then hyperconjugation. So mesomeric, then aromaticity, and then you have second, that is hyperconjugation plus extra resonance, and over here you have hyperconjugation plus 3 pi bonds. So this is the order. Is this clear to all?
Yes, ma'am.
Okay. Note this down, and all are these your homework. Note this one also. Okay. Now, on this page only, I'm writing that there is one extra stabilizing factor of carbocation. So, other factor for stabilization of carbocation is dancing resonance. Just a second. So, this is a dancing resonance. Okay. Now, carefully listen. What is dancing resonance? It is basically the conjugation of bent orbitals of cyclopropyl ring. This is a cyclopropyl. Propyl means propane, so propyl. Then cyclo because cyclic structure. So three-membered ring, cyclopropyl ring has a bent bond. Why? Firstly, try to understand this. You have sp3 hybridization of all the carbon atoms. Correct. And here you are going to have a carbocation like this, adjacent carbocation to the cyclopropyl ring. Now what happens? You know sp3 hybridized orbital. So the required bond angle is basically 109 and 25 minutes like this, right? But over here, you have only 60-degree bond angle. Correct. So due to the 60-degree bond angle, there is high angle strain. Okay. Also, when you are basically you are overlapping sp3 hybridized orbitals. Okay. So if I say that this is your sp3 hybrid orbital. Okay. This is your sp3 hybrid orbital. This is your sp3 hybridized orbital. Okay. So these are basically, so let it also overlap like this. So these are overlapping with each other. Okay. But as you can see, these are bent because when I say for the alkane, normal alkane structure, so if I say that these are the sp3 hybridized atoms, and obviously their orbital will be overlapping like this axially. Okay, in normal alkanes. But when you talk about the cyclic structure, these are basically bent bonds. These are bent bonds, and due to this bent bonds, they are very weak because these are bent. So these are very weak. So what happens? I'm rubbing this. So due to this bent bonds, firstly I'm writing the high angle strain. There is high angle strain, and these bent bonds. So what happens? I'm drawing it again. So this is the vacant orbital of the carbocation. Okay, having these two valencies. Hydrogen, hydrogen, I'm writing. Then I am saying that these are bent bonds. So basically, this and this, these one. Okay, all these are bent bonds, right? And each are having two electrons in each orbital. Okay, so what happens? Since these are very weak bond, these are bent bonds, overlapping is not that much great when you have a normal alkane. So these will donate its electron density to the carbocation vacant orbital. Okay, so you are going to have a resonating structure like this. Now you are donating this electron density, so obviously your ring will break. And why ring break? Basically to release this angle strain, to release this 60-degree highly angle strain. There was very high constraint. This structure is highly angle constrained. So to remove, to reduce this angle strain, you are going to open this structure. So here I can say this bond is broken down and there is double bond, double bond. as you say for the resonance part, that if you have this carbocation adjacent position, so you donate this electron density to this carbocation, so you make a resonating structure like this. Carbocation will be over here, single bond, because this bond will be broken down, and carbon double bond carbon. Similarly, this bond will be carbocation now, because here this carbon is not making any bond with any of the atom. This atom is making extra bond, that is the double bond. So here this is your resonating structure. Similarly, these electron can also be donated to this, so you can have one more resonating structure, not simultaneously, I am saying similarly. So here you can have one more resonating structure, like in this way. These will be intact and this is broken down, so this will be your carbocation. So these can also donate to the vacant orbital. Okay, so this is the dancing resonance. So dancing resonance is basically conjugation of bent orbitals of cyclopropyl ring and vacant orbital of your carbocation. So here I am writing down conjugation between bent orbitals of cyclopropyl ring and vacant p orbital of carbocation. Is this part clear to all?
Yes, ma'am.
Yes, ma'am.
Note this down. Oh, now let's see that dancing resonance case will lie in between which effects. So see, this is your question. So we will see through question. We have to again arrange these in the stability order of the carbocation. So you have carbocation and three cyclopropyl rings. So you can have dancing resonance from three rings. That is again highly stable. Okay. Here you have cyclopropyl ring 2. That means 2 dancing resonance. Here this is aromaticity and this is only one cyclopropyl ring. So your order is basically like this only. So I can conclude one thing, that strength of dancing resonance, because that is kind of resonance only. So strength of dancing resonance dr is in between mesomeric. So firstly, mesomeric is highly stable. Then you have to compare between aromaticity and this your dancing resonance. So mesomeric and aromaticity. So whenever you have dancing resonance from two cyclopropyl ring, till two cyclopropyl ring, you will give the priority to dancing resonance. But then you have to give the priority to aromaticity if you have only one cyclopropyl ring. Clear?
Yes, ma'am.
Okay. Now see the second question. This second question says you have carbocation and resonance from two phenyl rings. Right. Here you have carbocation and hyperconjugation because you can see these are only alkyl groups. So inductive effect and hyperconjugation. Inductive effect is weak effect. So we will give priority to hyperconjugation. So I will say that these are having 9 alpha hydrogen and here you are having resonance from two phenyl rings. Correct. Here you are having only one phenyl ring. Now I have told you one thing that resonance will be given priority to hyperconjugation. Correct. So here this is more stable than this. But now 9 alpha hydrogen is more stable than one phenyl ring. So in this case hyperconjugation is more stable. So whenever you have 9 alpha hydrogen, that is the highest case of hyperconjugation because you can't have 12 hyperconjugation, 12 alpha hydrogen. 9 is the highest one, right? So whenever you have 9 alpha hydrogen, you have to check that there are how many phenyls. If there are two phenyls or three phenyls, then always resonance. That is the normal order. But whenever you have only one phenyl ring, then it has been seen that the hyperconjugation one is more stable than the one phenyl ring resonance. So this thing also you need to remember this whole concept and this concept. When you have to give the priority to dancing resonance and aromaticity and when you have to give the priority to hyperconjugation or resonance. Done. So these are two questions for the exceptional behavior. Otherwise, you have to follow that order. Mesomeric, then it would be your aromaticity, resonance, hyperconjugation, inductive effect. Dancing resonance will lie in between mesomeric and aromaticity. Note this down. Done.
Yes, ma'am.
Okay. So this is for the stability. Now we are starting the reactions of carbocation. So in the reactions of carbocation, we are going to see three things. That is first, that is this rearrangement. Second is the different reactions. So addition reaction of alkene and alkyne. And third is your name reaction that we will skip for this chapter. Okay, these three are the parts of this reactions of carbocation. So firstly, rearrangement of carbocation. See, again, very important. So when you have CH3, carbon, phenyl, hydrogen, and carbocation. Okay, so this is CH2. So carbocation is on this carbon atom. Now, there are basically three possibilities. because I have three atoms, three different atoms. So here I have phenyl that can migrate to this carbon atom, and this carbon atom will bear the carbocation. Okay, see over here only one alpha hydrogen is stabilizing your carbocation. That's it. Only this is your alpha carbon. So only one alpha hydrogen is stabilizing. Okay, so now I have to make my stable carbocation through rearrangement because my carbocation can rearrange. So I am seeing those possibilities. So firstly, I am saying that I'll be shifting my phenyl. Okay, so I'll be shifting like this with both the electrons. So over here, CH3, carbon, hydrogen, carbocation, CH2, phenyl. Correct? This is your shifting. So this is the 1,2 phenyl shift. 1, 2 because here if I name 1 and 2, so this is 1, 2 shift. Okay. Now I have one more possibility. If I can shift hydrogen, so if I shift hydride, so basically H minus we are shifting, so I'll be calling it hydride. So if I shift 1 to hydride, so it is 1 to hydride shift. So I can write down CH3 carbon, phenyl, carbocation over here, CH2 and this hydrogen will come over here. Okay. And the next possibility can be I can shift this CH3 over here only. So it is 1,2 methyl shift. So this is phenyl, carbon, hydrogen, carbocation, CH2, CH3. Now I have to see that which structure is the most stable. So can you answer which structure is the most stable? Cation, which, sorry?
Second.
Second one, right. Because see, over here you are having alpha hydrogens only, that is 5 alpha hydrogen. Correct. Over here I am having 6 alpha hydrogen and resonance also. So here I have 6 alpha hydrogen and resonance also. In this case, I am having resonance and only 2 alpha hydrogen. Correct. So my most stable structure is this one only. That means I'll be rearranging my carbocation in this way only, not in this way, not in this way. I'll be shifting my hydride first to have a stable carbocation. So whenever you have a possibility to rearrange carbocation and make a stable one than the previous one, so you will always rearrange that carbocation. So you have to now understand this and keep in your mind that always see the possibility of rearrangement. Whenever there is possibility, you have to rearrange that. So just note this down and then I will discuss question with you all. Done.
Yes, ma'am.
Okay. Now see, first one I'll be discussing, second one will be your homework. Okay. So in this case, the carbocation is over here. Okay. So you can think that ma'am has said that you have to rearrange the carbocation. So you will what do? You will shift this hydride over here. Okay. So you will do 1 2 hydride shift and make oxygen, phenyl, and over here carbocation. Right. So now tell me, or you can shift phenyl also, but obviously phenyl one will be not stable. We have seen you have to shift the hydrogen one only if you have hydride. So just tell me the first structure is more stable or second structure is more stable. First structure, first one. Why?
When mesomeric effect is greater than
Correct.
resonance.
Over here, you have mesomeric effect, so there will not be any rearrangement. I have told you, you have to see rearrangement then only if you have second structure more stable than the first one. So second one is not stable, first one is stable through mesomeric, so I'll not be rearranging that, so no rearrangement. Okay. In this case, you have homework. Come to this third case. Over here, I have written this example just to tell you one thing, that you can have more than one rearrangement also. So over here you have carbocation. I can shift my hydride over here. So I can make my carbocation over here. This carbocation is more stable than this one. You can check hyperconjugation. Okay. Then I can see that there is nitrogen. So if I shift my carbocation at this place, I can have mesomeric effect. So yes, I'll be shifting again, and over here you will be having carbocation and it will be stabilized by plus M effect of nitrogen. So from this example, it is clear that you can have more than one rearrangement also. So just note this down. Okay. So done. Just a minute. Okay. Now the next rearrangement. These are also ring rearrangement, that is ring expansion and ring contraction. In that topic only, rearrangement of carbocation. So if I say that I have a cyclic ring, three-membered ring, and over here I am attaching OMe, that can have mesomeric effect, right? And I am drawing a carbocation over here. Now again, cyclic membered ring, three membered, four or five, all these are unstable because these have high angle strain. Okay, only six membered ring is perfect. Okay, so let me first draw. If you have four membered ring and a carbocation, if you have five membered ring and adjacent carbocation, and if you have six membered ring, adjacent carbocation. So this is 60-degree, highly angled strain. This is nearly equal to 90-degree, highly angled strain. This is nearly equal to 108. So angle strain is there. Okay, we say that yes, there is angle strain. Not that much as it was 3 and 4, but it is there. Here you have perfect 109.25. So it is clear that it is highly stable. So what is the significance of this? See, you have highly angle strained ring. So obviously it will tend to open up, right? So to open by ring expansion, basically it will expand its ring structure. Firstly, it is three membered. So what it will do? It will expand its ring structure to become 4-member, because obviously 60 degree is less stable than 90 degree. 90 degree is more stable, then 108 is more stable, then 109 is more stable. So what will 3-member do? It will change into 4-membered. 4-membered will change into 5, and 5 into 6. After 6, I will tell. So firstly, discussing for this 3-membered ring. So what will happen? Highly angled strain. So your bond will break. So adjacent bond will only break. So whenever I talk about resonance, if you have cation over here, so obviously this electron density only shifted to this one. You can't shift this electron density, right? It would be only adjacent one. So over here, this electron density will be shifted, or you can take this one. These are similar. So here I'll be shifting my electron density, that this bond will be broken down and this carbon atom will make bond with this carbon atom by donating electron density. So what happens? I am drawing the transition state so you can better imagine. If I have this one, I am saying this bond is broken down. So it is B I am writing. And now I am saying that this carbon atom is making extra bond with this carbon, that was this. So here you have a single bond and it is forming. So this is your transition state. Now carefully see. You have OMe intact. If I am breaking this bond and all the electron density is taken up by basically this a carbon atom only, because this is negative charge. So this negative charge is making electron, making bond with this positive charge. Correct. So obviously this carbon atom is now alone. It is not making any extra bond with any of the atom. So it will be a positive charge. Can you understand this? Why I'm writing positive charge over here and how ring expansion is occurring?
Yes, miss.
So I can write my structure that it is basically this one, this, and over here. So this is your, so if I just number it down, 1, 2, it was 3 and it is 4. Okay, so 2 and 3 bond is broken down. So 1, 2, it was 3, 2 and 3 broken down, but now 4 and 2 is made up. So here I can say it is a 4-membered ring. Okay, now coming back to the structure, third is having carbocation also and OMe also. So third is having carbocation also and OMe also. So here OMe and a carbocation, and this structure is now highly stable by plus M effect, and angle strain is also released. Is it clear, the ring expansion process?
Yes, miss.
Yes.
Okay. So now for the 4-membered ring, again similar case, adjacent bond will give its electron density to this carbon atom to have a 5-membered ring, because it is 4-membered. Just number it down, 1, 2, 3, 4, 5. Okay, so we will be having 5-membered ring. So let me just draw 5-membered ring. Now 1, 2, 3, 4, 5. Now you can easily see 2 and 5 2 and 5 bond is broken down. Yes, 2 and 5 bond is broken down, and 1 and 5 bond is formed. So 1 and 5 bond is formed. 2 is left alone. So it will have a carbocation. Done. Now for the 5-membered, similarly, you will be expanding this ring. So over here, it will be 6-membered again. So if I just write down, it will be broken down and this will be formed. Okay, so 1, 2, 3, 4, 5, 6. Make the structure 6-membered ring. 1, 2, 3, 4, 5, 6. 2 and 6 bond is broken down. 1 and 6 is formed. So yes, this is the structure. Second is left alone. So it will have a carbocation. It will have a carbocation. So this is the ring expansion for 3-membered, 4 and 5. Just note this down. Then I will continue this topic only. Okay. Now, on the next slide, I am writing for the six-membered ring. See, firstly explaining for three-membered ring. This example I have given by making a group, by substituting a group of mesomeric effect. Right. If you have only this one, then there will be no ring expansion. Why? Because this ring is highly stabilized by dancing resonance only. It will not be stabilized by ring expansion. But if you have any substituent that can give you mesomeric effect, then yes, your ring will expand and you will be having mesomeric effect and it is more stable than your dancing resonance. So you will expand your ring. But if you have only this ring, simple cyclopropyl ring having carbocation, no ring expansion because it is highly stabilized by dancing resonance. Okay. Now for the sixth case, six-membered ring, I have told you this ring is basically highly stabilized. Pure 109-degree, that is perfect tetrahedral structure. So here there will be no expansion again. But yes, if you have any mesomeric group that can provide mesomeric effect stability to the carbocation, then it will only expand. So here I can say one thing, that three-membered ring and six-membered ring have conditional ring expansion because these are based on condition. Condition is this, to have mesomeric effect. If you have mesomeric effect by ring expansion, then yes, they will expand, otherwise not. So three-membered ring and six-membered ring has conditional ring expansion if plus M is there after expansion, then only it will expand. Okay, note this down. Done.
Yes, ma'am.
Okay. Now the next case, that is ring contraction. Ring contraction, if you have here, wait, okay, this is the structure given to you and carbocation is over here. Now in this case, you are having carbocation over here only and you can't really migrate any bond. Okay, so basically now we will say that I'll be do ring contraction. How? See, this is the bond that can come over here. So basically, if you have one, two, three, four, five, six, six-membered ring is there. Now I am saying if I break 1 and 2 bond, okay, and 2 make the bond with sixth one, so only 5-membered ring will remain and one will be left alone. So it will have a carbocation, and yes, then you can have a mesomeric effect. So more stable structure, correct? Why I am doing this thing? Because here you don't have any atom that can show this rearrangement to go to this carbon atom. So I am now making the rearrangement of the bond, and rearrangement of the bond is basically ring expansion or ring contraction. Okay, so here this ring will be intact. Now I am saying I am breaking this 1 and 2 bond and I am making this 2 and 6 bond. And here your ring will be intact. Okay, so this is 6, 5, 4, 3, 2, 1. And 1 is having OH also. So 1 is left alone, so it will be your carbocation. So I can draw the structure like this. 6-membered ring. Here, this is your 5-membered ring. This is 6, 5, 4, 3, 2. And this is your 1. And 1 is having OH and a carbocation. So 2 and 1 is broken down. So this is ring contraction. Now you are making the ring contraction 6 to 5, but it is stabilized by plus M effect. Clear? Ring contraction.
Yes, miss.
Okay. Now one more case. If you have 7-membered ring. Okay. If you have 7-membered ring, here is your carbocation and this is your valencies. Okay. Now this is your 7-membered. So basically you can rearrange your ring by making to 6-membered ring. How? If you can say that I'll be making rearrangement of this bond and it will make the bond with this carbon atom. So this will be left alone and it will be a carbocation, and this carbocation will be highly stabilized by more hyperconjugation, and your ring will also be stabilized because it will change into 6-membered, because again 7-membered ring is also unstable than 6-membered, because 7-membered ring is basically expanded ring. You have to maintain 109 only. So expansion also have to be, also there will be angle strain to maintain that 109-degree angle. So again 3, 4, 5 highly angle strain, then after 6 again highly angle strain ring. So we have to make the ring contraction to make my ring more stable. So if this is 1, 2, 3, 4, 5, 6. Okay, so 1 is having extra methyl, 2, 3, 4, 5, 6. Correct? Now, this carbon atom is broken down from 2, correct? But it is attached to 1 only. So, if I am referring it is as A, so A is attached to 1 only, right? But 2 is broken down. So, over here you have 2 methyl groups, and since it is alone, so you have a carbocation over here, and now it is highly stable from your 6 alpha hydrogen, and you have a 6-membered ring that is highly stable than 7-membered ring. So this is again ring contraction case. Okay.
Yes,
Note this. Done.
Yes, ma'am.
Okay. Now there are again different type of rearrangement. If you have So other types of rearrangement. If you have bicyclic ring, like I'm having four-membered ring, attach four-membered ring, but carbocation is over here. Okay, now I have to rearrange. So see, four-member ring, highly angled strain, so it will tend to open. Ring expansion will be there. So similarly, we have done that it will expand. This will not expand because it is on this carbon atom only. This is adjacent, so it will expand first. That is this ring. So over here, it will expand and it will form the bond. So if I have one, two, three, four, and if this is your five, so over here, this is your four-membered ring. Now, this is your 1 and 5. So, 1. So, basically, a 5-membered ring will form. So, I'm making the 5-membered ring. Now, this one was your 5 number. Then 1, 2, 3, 4. So, 1 and 4 is broken down. Yes, 1 and 4 is broken down. And 4 and 5 is formed. So, 4 and 5 is formed and 1 is left alone. So, it will be having carbocation. Correct? Now, you can see that now for this ring, that is the second ring, this ring is adjacent to the carbocation. Now it can also expand by donating its electron density to this membered ring, and you can say this will also be 5-membered. So over here I can write down that, okay, so let me just make in this way, that if I number it down, 1, 2, 3, 4, and this is your 5. Okay, I'm writing this down like this. So if I have this ring, so this was 5. I'm writing this one, right one. So 5, 4, 3, 2, 1. Okay. Now I'm making this ring expansion. So 1 will make the bond with 5 now. And 5, your fourth will be alone. So over here, 1 will make the bond with 5, 1. And you can have like this structure. So this will be left alone. So here you will be having a carbocation. This is also a 5-member ring. 1, 2, 3, 4, 5. And this is also a 5-member ring. So I can write down more simplified structure because you have a fused ring. Two carbon atoms are joining together. So I can draw this structure. This is same to this one, just a simplified version. And you have a carbocation at the fused carbon. So yes, you have a carbocation and fused carbon. Now you don't have any ring expansion. So now there will be only one thing, that you can have any product. If you have a nucleophile, that nucleophile can attack on this one to make your product. That we will discuss in reaction mechanism what will happen in the product side. Or you can have no electrophile, no nucleophile. So then there will be the case of elimination. So here I am just writing down the product. I will explain in the reaction mechanism part. So this is your major product for the elimination case. If you don't have any nucleophile, this is in the presence of nucleophile, what will happen? And this is the absence of nucleophile. So is this part clear how I am doing the ring expansion for the bicyclo ring? So one short trick you can just remember. Otherwise, you should know how to do this mechanism, because again, question can be framed from the mechanism part also, that how many structure has carbocation like this in the steps. So you have to make the structures and then you have to count that two structures are having mainly carbocation in your steps. So the trick is this, that if you have like this structure, so you can make both the rings higher membered ring. So 5-membered, 5-membered. I can say this will also be 5-membered. This will also be 5-membered, and it will be fused only, and fused one will have carbocation. So this is the trick. That like only you have to make one higher member ring, and fused one will have the carbocation. But you should know how I am doing ring expansion, because this is a very basic part of this carbocation. Note this down, then I will discuss for 5-member ring also. Okay. So now, if you have five-membered rings, so five-membered ring having a carbocation and single bond, five-membered ring. So if you have this thing, then again you have to make higher membered rings. So you have to draw all the structures. I am writing down directly the product. You will be having six-membered ring, both the six-membered ring, and they will have a carbocation at fused carbon atom. You have to draw all the structures. That's your homework. You have to get this structure as your product. So this one. But now if you have six-membered ring, so over here you don't have any ring expansion. You don't have any ring expansion because again this is stable. Six-membered ring is stable. There will be no ring expansion. For 4, 4, for 5, 5, you will be having ring expansion in this way. Just note this down. Hmm? Okay. Now we are starting with the reactions. So the first reaction is the dehydration of alcohol. Dehydration, hydration is water, that is supplying water. So dehydration, removing water. Okay. So dehydration of alcohol, basically I'll be removing my alcohol in terms of water only. How? See, if I have this alcohol, secondary alcohol. I'm not writing hydrogens, just write them and balance them. So this is your structure OH on the secondary carbon atom. Okay. Now the reagents are acids. So if you have H2SO4 or if you have H3PO4, so basically I'm providing H plus. Okay. So if you add H plus, so what it will do? H plus is electrophile. OH is your nucleophile. So it will take up your H plus. So over here, if I am supplying H plus, so oxygen will take this H plus and it will form carbon, carbon having OH2 positive charge and carbon. Right. Now, oxygen having positive charge, not stable, it will remove. And you are going to have a carbocation on this carbon atom. Right. And this is your rate determining step. Rate determining step. So it means that formation of carbocation is directly proportional to your rate. More stable is your carbocation, more rate of dehydration. Can you relate to this? Rate determining step and the stability of carbocation. So here I can write down that rate of dehydration is directly proportional to the stability of carbocation. Okay, so this is the one thing. Now my carbocation is formed. And afterwards, what will happen? That we will do in reaction mechanism, that if nucleophile is there, it will attack. Or if no nucleophile is there, so your H will basically remove. H plus will be removed and it will donate like this to have elimination product. Otherwise, it will have a nucleophilic attack. But now the main concern is for the intermediates or this mechanism, not the product side. Product side we will do in the reaction mechanism part. What will happen? So this is your dehydration product, because dehydration of alcohol, because I am removing alcohol in terms of water only. H2O is removed. Done. So this is the one thing. Now next thing that I have to tell, that here I am forming the carbocation, right? So in carbocation we basically see that firstly you have to form the carbocation, right? Then you have to check its stability. Then go for the stability. Okay, so basically I'm telling you how to write the product, how to write the major product. Okay, so firstly you have to form the carbocation, then you have to see the stability of carbocation, and then you have to see the possibility of rearrangement. then only you will get the correct answer. Possibility of rearrangement. So you don't have to forget about the rearrangement. You have to follow that if there is possibility for the rearrangement, you have to make that product, make that carbocation stable. So these three things you need to clear. Okay. Now this is the question. I'm discussing this one and all will be your homework because again, same that we have done ring expansion, all those mechanism, it will come over here now. So see, you have OH. So again, phenyl, C, carbocation, CH3. Okay. So I can say that, okay, let me write down CH3 and this is CH2. So I can say that carbocation over here is stabilized by 5 alpha hydrogen. Correct. But if I have hydride shift and I have a carbocation over here, I can imagine that it will be more stable by resonance. So obviously there will be your 1,2 hydride shift, so that rearrangement part. So over here, I'll be making this carbocation and it is very much stable because now it has 2 alpha hydrogen and resonance also. So now it is more stable here and then it will form your alkene, that is phenyl C double bond C CH3. This is your product. So carbocation is on this carbon atom, not on this one. So you have to see the rearrangement part. So this is our product. Done. I am discussing this one also. H2SO4 OH. So yes, it can accept H plus. Over here, I can have my, so basically now the trick is just remove the OH. If you see H plus and OH, just remove the OH and make a carbocation. Because now I know it will be removed and you will be getting carbocation over here. So I'll be getting a carbocation over here. Correct. Now, can I make my carbocation more stable through any rearrangement? Just tell me, can I make my carbocation more stable through any rearrangement? Answer is no, because over here there is no mesomeric effect. So by ring contraction, I get mesomeric effect, so it is more stable. No, no mesomeric effect. And also, if you make a carbocation over here at this center, there will be less hyperconjugation than this one. It is having 4 alpha hydrogen. That is the greatest one. So no rearrangement over here. Simply you will write one alkene is this that can form, or it can form plus it can form this alkene, that is this hydrogen can also leave, H plus can also leave, and over here now tell me which one will be major and which one will be minor, first one or second one, which one will be major one? Product. Just note this down and then tell me.
Second one.
Sorry, second one is major one, major or minor?
Major.
Yes, correct, major, because more alpha hydrogen. Here you have 4 alpha hydrogens of alkene, and here you have only 3 alpha hydrogen of alkene. So obviously this will be your major product and first alkene is your minor product. Note this down. Done.
Yes.
Yes.
Okay. Note this down. This is your homework. Again, you have to remove OH, make a carbocation, and this rearrangement we have already done. You have bicyclo and carbocation. You know how to make a product. This is also your homework. Firstly, you have to make a carbocation and then you have to see which carbocation is more stable. So you have to see the rearrangement and then make a product. I will discuss in the next class all these homeworks. Noted?
Yes.
These are also your homework. All these are very simple. Just you need to follow the process. And you have to make the last product that is of alkene. By removing H plus, you have to see which alkene is more stable. If you have two possibility, then you have to see the hyperconjugation. Okay. Now come to this question. Over here it says which rate is more. So basically which compound has more rate. Okay. So the first rate is given and you have alcohol over here and alcohol over here. So whenever rate is asked, okay, so then we never consider rearrangement. Because obviously, if the question is saying that you have to see the rate, then you have to see the original product, original molecule only. Because here, if I remove OH and here, if I remove OH, I'll be having my carbocation over this and I'll be having my carbocation over this. Now, if you say I'll be doing rearrangement, then you will be making second structure only, same structure. So you will say K2 is equal to K1, but that is not the thing because question is given this thing. So if rate is asked, you will never do rearrangement. You have to see the original structure. Now tell me which rate should be more because now you know how to compare the rate. K2, right? So K2 is greater than K1 because rate is directly proportional to the stability of carbocation. Over here, carbocation is having 1, 2, 3, 4, 5, 6, 7. So 7 alpha hydrogen and over here you are having only 1 alpha hydrogen. That is why. Note this down. Done. Okay. Now the next reaction of carbocation only that is diazotization of primary alkene. Sorry, primary amine. Primary NH2. Diazotization, I will explain. See, the general reaction, if I write down, it is RNH2. This is the primary amine. Okay. Over here, if I add my reagents, what are the reagents for diazotization? It is sodium nitrite NaNO2 in the presence of acid HCl. Okay. Or you can say HNO2 nitrous acid. Okay. These are the two combination. You can be given any NaNO2 plus HCl or HNO2. These are same only because if I talk about the mechanism, so if you have NaNO2 and HCl, so obviously they will combine to form HNO2 and NaCl. So this is same. You can be given this or this combination. Now, by adding this reagent, your NH2 basically becomes a very good leaving group, N2 positive. I will explain how by the mechanism. So now nitrogen having a positive charge, highly unstable, so it will leave. And now it has become a very good leaving group. Firstly, it was a bad leaving group. NH2 is a bad leaving group because it is a good base. When we study about the reaction mechanism in alkyl halide chapter, I will tell you what I have written. Bad leaving group because it is a good base. So there I will tell you about the leaving group. So basically leaving group are good leaving group when they are weak base. If they are strong base, then they are very bad leaving group, poor leaving groups. Okay. So about leaving group, we will discuss in detail in alkyl halide chapter, reaction mechanism. So this is the thing. This is bad living group. We are changing to good living group by adding this reagent. Now it has become, so it will leave to form a carbocation. Now again you have a carbocation. So you have to see the stability, you have to see the rearrangement, all those things again. And then if you have, so basically there is internal nucleophile only, water, and you are going to have alcohol. So what is the final product of this reaction? Diazotization, it is alcohol. Always alcohol. If it is mentioned water, then also alcohol. If it is not mentioned, then also alcohol only. We will see that water is basically internal nucleophile. It will be given out from the mechanism part. See, so in the mechanism part, you can be given NaNO2 or HCl or HNO2. Okay, so let's write down if you have HNO2. So if I have nitrogen, double bond oxygen, OH. This is your structure of HNO2, right? And acidic medium is provided, so it will be H plus. You have OH, that is your nucleophile that can take up your H plus. So it will take up the H plus to become a good leaving group. So OH2, positive charge, nitrogen, double bond oxygen. Right. Now water is a good leaving group. It will leave. And you are going to have nitrogen, positive charge, double bond oxygen. And what is this? This is your electrophile of this reaction. Diazotization, nucleophile is NO positive. Clear? Now, you have aniline. So here over here you have RNH2. Okay, and you have a nucleophile also, that is NO positive charge. So aniline having a lone pair that can donate, and it is nucleophile, it is electrophile. It will interact, it will donate its electron density to nitrogen. So it will form RN H positive charge because it has donated its electron density. Nitrogen will be neutral now, double bond oxygen. Right. Now there will be obviously nitrogen having a positive charge unstable. So what it will do? It will lose its proton. And this proton will be given out and this proton will be accepted by this oxygen only. So it will accept this proton. So this is basically proton transfer. I am transferring my proton from one atom to another. This is proton transfer. Okay, so I can say R, nitrogen, NH, single bond, nitrogen, double bond, oxygen, H, and now it will be positive charge on the oxygen atom. Why? Because oxygen has donated electron density to accept this proton that was removed from the nitrogen. Clear till here? Okay. Now again, oxygen having positive charge, highly unstable. So what it will do? Nitrogen will donate electron density to this adjacent nitrogen single bond, nitrogen bond, and this electron density will be shifted to oxygen to neutralize the positive charge. So nitrogen, positive charge, hydrogen, double bond, nitrogen, OH. Done. Now I'm writing over here. Again, the similar case, there will be proton transfer because nitrogen having positive charge, unstable, it will lose this proton and this proton will be accepted by this oxygen only. So what will happen? R, nitrogen only, single, double bond, nitrogen, OH2 positive. Now if you can see, I have made my OH as a good living group. Nitrogen will again donate the electron density to this bond and water will leave And here I have my internal nucleophile, that is water. Okay, so I have my Rn double bond nitrogen positive charge. So that is why I am saying it is Rn2 positive charge. That is this thing. So this nitrogen having positive charge unstable. So what it will do? It will leave. So if you have this thing, so it will leave to form a carbocation like this. Is it clear? The mechanism part of this diazotization?
Yes, ma'am.
Okay, just note this down. So that is why I was saying that if water is not mentioned, then also water will be there because water is over here. It is removed from this mixture. So water is present as internal nucleophile. It is internal nucleophile. It will attack on your carbocation. It will have the final product as alcohol.
No, you can proceed.
So all these questions are again your homework because I can conclude one thing that whenever you have any lean and a reagent HNO2 or NaNO2HCl, then you will be forming carbocation because you have to remove this NH2 and carbocation will be formed over here. So if this is R, okay. And one more thing that we have done from alcohol part, if you have alcohol and any acid that is providing your H plus, so again you will be forming carbocation. So all the reaction will be similar. You have to form the carbocation, you have to see the rearrangement and make the product. And for diazotization, my product is alcohol. And for alcohol part, my product is basically alkene if you don't have any nucleophile. If you have nucleophile, that nucleophile will attack. So all these are your homework. Okay, just a second. This is your 17th slide. Okay, now see this question. So you have this type of rearrangement, this type of arrangement, and it is given any your amine and this combination that we know that it will form your N2 plus and a carbocation, right? And it is mentioned that you are having two different type of product P and Q, and you have to tell the relation between them. So basically this question includes stereochemistry. Over here I am telling you about stereochemistry so that you can relate when we will complete that stereochemistry and you will revise this chapter, so you can relate both the topics because question is asked from the stereochemistry only. So that is why. So over here, you have to remove this NH2 plus, correct? And you have to make a carbocation. So if I am writing, this is your ethyl, this is your hydrogen, and this is your carbocation. Now, in the first slide only, I told you that carbocation sp2 hybridized trigonal planar means now your molecule is trigonal plane, correct? So I can say one thing that my water or your nucleophile, this is what your nucleophile. So your nucleophile can basically come from above side also or it can come from below side also. Can you say like this? If this molecule is on plane, then I can say my nucleophile can come from above the plane or it can come from below the plane. Right?
Yes, ma'am.
So here I can draw this structure CH3 ethyl. If it is coming from above the plane, so I'm mentioning that it is coming from the right side. Okay. And if it is coming from the below the plane, so I'll be mentioning that it is coming from the left side. So CH3 and ethyl will be same. You just have to rotate your hydrogen OH. If it is coming from this side or it is coming from this side. Okay, because this molecule is your planar molecule. So now you have two different types of molecules. So yes, you have P and Q. Now you have to tell the relation. So here I am telling you the answer. When we will read stereochemistry and read when you will revise this one, you will get the concept that these are enantiomer. So enantiomer, if in just I talk about, these are basically mirror images that are non-superimposable. Okay, so if I have OH over here and OH over here, okay, and if I place a mirror in between the molecule, so you can see that OH is over here and OH is over here. So yes, these are mirror images to each other. And if I place this molecule, okay, so if I place your right molecule on the left side, so obviously you will get this structure that are non-superimposable. These are non-superimposable. So that is why what are enantiomer? These are mirror images to each other and non-superimposable. You cannot superimpose two molecules. Okay, so these have the relationship. These are enantiomers. Note this down, then I will discuss this question. Second one. Done. See, now the second question. You have NH2 over here. Just remove this NH2 because you have HNO2. So remove this NH2 and you have a carbocation over here. Right. Now, this carbocation is having a hyperconjugation. Okay. But can you see there is this 4-membered ring in between? So this structure has a possibility for ring expansion. because 4-membered ring can easily expand to 5-membered ring, and these are adjacent only. So basically, this electron density can be shifted to this carbon atom. So you can have 1, 2, 3, 4, 5. So I am saying that I'll be making 1 and 5 bond. So 1 and 5 bond. This is your 5. This is your 1. 5 attached to your 4. Correct. 3, 2. Your 2 and 5 is broken down. And these are formed. So I can say your structure is now like this. You have a 5-membered ring on both the sides that is more stable. Correct. So over here, since 2 is left alone, it will have a carbocation on this side, and my last product. So this carbocation is highly stable now. So you can't say this thing that, ma'am, I want to shift this methyl to have a carbocation over here. So, okay, let me write down that concept. If you shift Me and you make a carbocation on this structure, so over here, you will not have the stable one because this carbon will become sp2 hybridized, and I have told you this should be always sp3 only. No sp2, no sp. That is why no shift. So this carbocation is stabilized over here only. So you get your final structure as alcohol over here. So this is your product that you will get in the option. Done? Is this clear to all? So you can have ring expansion like this also. You have to see the possibility.